So I've been working on this rig now and done for the past few days. And as you can see, it is a small VESC HD. No, it's not an HD, it's a VESC Edu that is connected to one of those small 5010 BDUV brushless motors. This is not a great motor. You can see the copper fill there is, you could have a lot more copper fill in this one, for instance, and you could have better bearings and it could be balanced. It's really wobbly when it runs, but it does work. And this is a load cell from a kitchen scale, a 5 kilogram kitchen scale, and this board here is a breakout board for one of those 24-bit ADCs that is connected to I2C, and that I2C plugs into the COM port of the VESC Edu, and I will use the scripting to interface this load cell in this demo then. Also note that there is no sensor in this motor, so we are running completely sensorless, and we are going to try to rely on HFI to get full torque and measure the torque actually in this rig. So the idea is here that you have a known distance from the center of the motor to where you touch the load cell, and then if you know the distance and you can calculate the force that presses on the load cell, then you can calculate the motor torque. And if we look at my CAD drawing of this one that I did to print the parts, I have put the sketch on this side here, and this dimension is just what it turned out to become when I just placed all the parts and drew everything around it. So you can also see the arm here. The center of the arm goes in line with the bottom side of this one, and then this peg on the load cell is on that line, so you should have a straight line from the center to this point here. And there's a quite small point of contact out here, and it is in 90 degrees to the rotation center, and this is where this distance is measured. So to measure the torque of the motor, you take the force here in newtons and multiply it by the length of this arm in meters, and then you get the torque in Newton meters. And let's have a look at the code for this one. So here is VESC tool, and if you go to the packages, and you can also see this on GitHub, there's this NAU7802 driver, and this is the ADC on this I2C board that was talking about. And there's also some demos included here, and this one, for example, this demo measures the weight of a load cell when you calibrate it like this. And that is what I have taken here. So when you start this code, then it will zero the offset, and then I also added some like this one, cal with weight function, so you can calibrate what a certain reading translates to in weight. And also if you look at the video again, where did it go? This one. Then I also made another thing here, where I can mount the load cell with this cup. And then I just placed different known weights in here, or I knew the weights because I measured them with a different scale. And I used this to check, firstly, if it's linear, and then secondly, to get the coefficient of the DC reading to convert it to weight. And it turns out that these load cells are very linear, so they are behaving really nicely to measure weight. So given that my other scale was somewhat accurate, then we should have a pretty good weight measurement here. Then for the motor, I just took the default parameters on the Edu, which is 20 amps current limit, and then I ran detection from this page actually, so resistance, inductance and flux linkage, and applied, and then I just switched sensor mode to 45 degree V0 V7 HFI silent, so this is the silent HFI mode. And as it turns out, this motor works really well in silent HFI. I can show that quickly here. So I have a keyboard control active, and let's see, I think you can see the current down in the corner here as well. You can, let's see, I think I have a box. No, I have to actually activate keyboard control. So you can see this is 3 amps, and it really doesn't cog at all. And if I do the other direction, it wants to go in this direction. And even if I put it here and do duty cycle control so that we get more current, and I go all the way to 20 amps, it doesn't struggle at all with that. And you can also see, if you have a look at the rig here, you can see that it's bending when I do that. So there's a lot of torque applied. I cannot do that for long though, because this motor will heat up really fast if I give it 20 amps. So that's the rig, or that is the motor running HFI. And then we go to the development tools, and this is the code. So essentially from up here to down here, this is the thing from the demo. The only thing I did here, as I will explain why later, is that this loop that does those readings will run in a separate thread, so that we can continue here and do some plots after. And then to get the torque on the motor, we just multiply, as I said before, the grams or divide the grams by 100, because that's how you convert grams into newtons, because 10 newtons is 1 kilogram. So you have to divide the grams, well, 1000 grams is 1 kilogram, so you have to divide the grams by 100 to get converted to newtons. And also have a negative sign here on the 0.01, because it actually, when I push it down, it will get a negative number. So that's how I make it positive. And then we have the newtons, and we multiply the newtons with the length of the arm in meters, as we saw from the CAD model, and then we get the torque in Newton meters on the motor shaft. And then I draw that here. And if we select this variable here and go to the plot here, you can see that this will give us a number. And now if I use the arrows to control the motor, you can see that we can measure the torque. Now there's also another way to get the torque in the motor, and if you know the motor parameters, then you can calculate the torque from the current that you run in the motor. And if you look at that equation, it depends on how you set up your Park and Clark transforms and everything, but if you do it like this, then you will end up like the VESC is, like it's done in the VESC, then you will end up with this torque equation. And you have 3/2 times n, which is the number of pole pairs, and then you have this expression here. This essentially takes the salience into account, so if you have a difference in D and Q axis inductance. But if you don't run any D axis current, or they are the same, then this actually simplifies to just the Q axis current times the flux linkage in Webers. And that is what I have entered here. So I made this function called calculate torque, and then we can see that it just comes from this equation. See if I can show them at the same time. Yeah, I cannot grab the window like this, so maybe. Yeah, so you see that 3/2, that's 1.5, and then we get the number of motor poles. This also assumes that an additional info here that you set the correct number of motor poles, and this one has 14 poles, this particular motor. And this is supposed to be pole pairs and not poles. We divide it by 2 or multiply it by 0.5. And you can also see that the multiplication operator here, you can just give it a list of arguments that will multiply all of them together. So that way we can just write it in one expression. And the next we take the motor current. And this is the Q-axis current if you don't have MTPA or field weakening inactive. We can also do get IQ, but this one will not be, well, since I have inverted the motor direction, this one will not be inverted, so this will give us a negative torque, which also could work, but I'm just gonna do current here. And then we multiply it by the flux linkage, and this one, as you can see in the, if you open the documentation, you can see that this actually gives the flux linkage in milliwebers if you do conf-get. So you have to multiply it by, or divide it by 1000 or multiply it by 0.001 to get it in Webers. So this is the flux linkage. So if you run this calculation, you can calculate the torque according to, well, motor theory and whatever parameters the VESC measured. And that's what I have done here. And then when we run this code, we can see that the measured torque is just called torque here, and the calculated torque is according to this formula. And now if I run it in current control, yeah, I think I just moved the arm a bit, so it slammed into the scale a bit. Got a bit of offset there. But you can see that when I press upwards, they are, I can plot both actually, they are very similar. 1 amp, 2 amps, 3. Here we start to get some difference up in 11 amps. Actually, they are quite similar still. So you can see that it checks out quite well. And now that this works depends on a couple of things. It depends on measuring the motor parameters accurately. It depends on measuring the current accurately. And it also depends on, in this case, the HFI tracking the motor accurately and giving it a good angle output so that we can give it the correct current vector when it's standing still. So now that we have this, it would be nice to actually plot both torques, both the calculated and the measured torque against current, and it will also be nice to divide them by each other to see how close we are to, well, having a ratio of 1 between them. And that's the code I have commented out below here. So we'll just uncomment this block, and what we do here is you can see that now this thing is running in a thread, so we have all of those things available all the time, so we can use them if we continue the code here. And what we do is we first initialize the plot, so those plot init diagraph functions is on. Those will make a plot if you go to data analysis, real-time data, and experiment. And here you can see one of my runs here that will generate now. So we create a plot with current in the x-axis and newton meters in the y-axis, and then we add 3 graphs to it: calculated, measured, and ratio. And then we make a loop here. We loop from 5 to, let's see, 120 here. And the idea here is that we take this number and divide it by 10 so that we can get this as a current. And this will then be from half an amp to 12 amps. And then I make a local environment where I just take the I and multiply it by 0.1. So we divide it by 10 here. And then we set the current, and then we sleep for a bit. I could do sleep, but then it will time out, so I will just loop for a while and do timeout reset so we don't... We could also activate heartbeats here and just do sleep here, but this way we don't have to activate heartbeats. And then we should have settled that is current and torque on the scale. And then we select graph 0, which is this one, and then we send the current now and calculate the torque, and then graph 1 and send the measured torque, and then we set the ratio, and which should be 1, and we divide the measured torque by the calculated torque. So now with this uncommented, let's press stream, and also notice when I run this it will calibrate the 0 offset again. So let's try it. And now you can see that the motor is running. Actually, if you go to real-time data and experiment here, then you can see the experiment running. And you can see in the beginning here, as it runs, we had a bit more than 1 here, but that's probably because we only had half an amp and the weight of the arm itself pushed down a bit on the scale. But across the entire experiment, I mean, the torque drops a bit as we go up in current, but not that much, and we can see soon when it stops how much of the expected or the calculated torque we had left at the end of the experiment. And if we zoom in here, we can see that we had, according to this one, a bit over 88% of the torque left. And I actually have run this all the way up to 20 amps before. I will not do that now because the motor started smoking almost because it got really hot from that. But it actually continued, it didn't go down that much anymore when it kept on going here, so it seems like this one can push quite a bit of torque for a short while at least without overheating. And now a few observations. So we can see that the graph has a downward slope. This could be either because the motor is saturating or because the HFI is not tracking it as well when they go up in current, or it could be because of both things. I think it's more because of the saturation. I have verified that with a different motor with an encoder, but I haven't done it on this one. And also, I mean, even so, it doesn't drag. It goes from 100% to 90% or so of the torque, which is really good actually. And we can also see that is the slope, so it means that it's decreasing slightly, but it's staying almost within the same value. And also it's almost 1, or it starts off at almost 1, which it should do at low currents. So it looks like the math is checking out when we measure this using 2 completely different sources, like the current and flux linkage and motor equations, versus the load cell and the length of the arm of the motor, and converting that to a force in newtons, which is really interesting. And I mean, this rig might not be super useful. Well, if you have an encoder and you want to test and really get to know your motors properly, then it can be very useful. But you can also see that you could make something with load cells for propellers, for example. And I think a propeller rig is much more useful than this one, because it's difficult to calculate thrust of propellers, because you have so many turbulences and things influencing that. So if you just make a rig where you have a motor attached on a propeller with the load cell and try it over a certain load range, then you can plot those graphs nicely using the scripting and everything in VESC tool. And you can even export it to CSV later if you want to, or XML if you want to save the data and compare it at some later time. So yeah, a lot of new possibilities with the silent HFI and the scripting and all of the things coming to firmware and VESC tool version 6.